Hey Ramblers, this video covers chapter 9.3 in our textbook, and it's titled The Altitude to the Hypotenuse Theorem. It's a pretty daunting theorem if taken verbally, but once you let me walk you through where the theorem comes from, and you see the shortcut that it all boils down to, it really isn't quite as intimidating. The theorem is based on the similarity between the three triangles created when you drop an altitude to the hypotenuse in a right triangle. But I want you to be careful. While this video explains where the relationship comes from, I don't want you to feel that you have to reprove the similarity every time you come across a problem involving the altitude to the hypotenuse in a right triangle. It's really the shortcuts that are important. So let me walk you through it, see where they come from, and then the notes that you should be taking moving forward would be the final three relationships that I'll point out at the end of the video. Okay, take your time with this one, pause often, and take good notes. All right, thanks for watching. Chapter 9.3 investigates the relationship between the three right triangles, two of which were created when an altitude is drawn to the hypotenuse of a given right triangle. So let's say that triangle ACB is a right angle. It's a right triangle with the right angle up there at C. If I draw an altitude down to the hypotenuse AB, I will of course create two right angles, one on either side of the altitude. So now I've created two new right triangles. And the question is, are they similar to the original right triangle? And the answer is yes. Because you see, angle A in the blue triangle is the same A that shows up in the large triangle. So by angle, since A appears in both, and since both D and C are right angles, triangle ACD is similar to triangle ABC. Now the same relationship works between the second two triangles. Angle B in the large triangle ABC is the same as the angle B in the orange triangle. And once again, since angle C and angle D are both right angles, ABC and CBD are similar by angle as well. And this brings us to the final similarity, which is between the blue triangle ACD and the orange triangle CBD. Now, it starts with the angles. Since the blue triangle ACD is a right triangle, angle A and angle ACD are complementary. Now, since the orange triangle is also a right triangle, angle B and angle BCD have to be complementary because those two angles must add up to 90 because this is a 90-degree angle here, and we know that all three add up to 180. So A is comp to ACD, B is comp to BCD, and by virtue of the fact that angle ACD and BCD make up this right angle at C, we know that ACD and BCD are also complementary. So what does it all mean? Well, it means that angle A has to be congruent to BCD, and angle B has to be congruent to ACD. If that's not making much sense, let's try putting in some angle values. Let's just say that angle A was 30 degrees. And if that were the case, then it would have to be that angle ACD was 60. We know that that's a right angle at C, so angle BCD is equal to 30 degrees, which means angle CBD has to be 60. All right, so now it's a little clearer and easier to see that angle A and BCD are congruent, and angle B and angle ACD are congruent. So triangle ACD is similar to triangle BCD by angle. Okay, well, where does this leave us? Well, because of the special relationship between these three triangles, they become an important part of our geometry in the second semester, and certainly for proving the Pythagorean theorem in the next section. So we've given some special names to the parts of this triangle to help us remember the relationship. And it starts like this. The side that is opposite angle A in the large triangle we refer to as leg A. The side that is opposite angle B, again in the large triangle, we refer to as leg B. And the side that is the hypotenuse we just call the hypotenuse, and that's opposite angle C. Now, when we drop the altitude, which we'll refer to as the altitude, it divides the opposite side, the hypotenuse, into two parts. One part is part B, and that's named because it's next to leg B. The other part is part A, because that's next to leg A. So, let's take a look at the proportions created by the similarity statements, and then we're going to substitute in these labels. And we'll see that, in fact, we get some pretty easy to remember formulas that we'll be able to use throughout this chapter. Looking first at the similarity between the blue triangle and the black triangle. ACD is similar to ABC. Well, what's interesting about that is rather than writing out all three ratios, I can see that AC comes up in the ratio for AC to AB and the ratio of AD to AC. So if I multiply that out using the means extremes product theorem, I see that AC squared equals AD times AB. Now if I substitute in this alternate labeling, I see that leg B squared equals part B times the whole hypotenuse. That's just subbing these labels into this equation here. So that means that the square of leg B is equal to the part of the hypotenuse right next to it times the whole thing. Let's take a look at the black triangle to the orange triangle. And again, I set up only two of the three proportions or ratios because I see that CB shows up in both. It's the mean proportional between AB and DB. So by the means extremes product theorem, I can multiply and I see that BC squared equals DB times AB. In other words, using the alternate labeling, leg A squared equals part A times the whole hypotenuse. So it's these formulas down at the bottom that I really want you to focus on and to take notes on. And rather than try to figure out which one's leg A and which one's leg B, just think of it this way. Either leg, when you square the length of it, is equal to the part adjacent to it times the whole hypotenuse. And that goes for whether you're talking about leg A or leg B. Alright, let's take a look at what's left then with the final similarity, where the blue triangle is similar to the orange triangle. Setting up the proportion, I can see that CD squared, which is the altitude, is equal to part A times part B. So those become the real important part of this section. So I'd like you to memorize, make sure these are in your notes, that the leg squared equals the adjacent part times the whole thing. That is, and that's what it boils down to. As a result of these similar triangles, we know that the leg of the large triangle squared equals the part right next to it times the whole hypotenuse. Okay, I'm going to give you a page with all the important notes synthesized on it, and then I'm going to show you a couple of examples from the book. Okay, it's very important that you get to recognize this figure, this altitude drawn to the hypotenuse of a right triangle, and that you are able to pick out what the relationships are. And I think that you may run into trouble trying to figure out which one's leg A and which one's leg B and which one's the hypotenuse. Well, that usually sticks out at you. But try not to do that. Rather than reprove all these similarities and set up those proportions, for this there's a great shortcut. Just remember this, that either leg of the large triangle squared equals the part of the hypotenuse right next to it times the whole thing, and that the altitude squared equals the product of the two parts. That way you really don't have to worry about whether you're talking about part A and part B or leg B. Just remember these two formulas. Okay, let's take a look at a couple of examples and then we'll conclude the video. Suppose we're given that triangle ABC is a right triangle, and they tell us that BD is an altitude. Well, that's exactly the situation we're talking about. If we knew that AD is 4 and CD was 9, can you find BD? Well, we recall from what we proved in the video that I can jump right to the shortcut, that the altitude squared equals part A times part B. Now, it really doesn't matter whether AD is part A or DC is part A. All I care about is plugging in and getting my answer. So x squared equals 4 times 9. So x equals positive or negative 6. But in this case, since we're talking about an altitude, it can't equal negative 6. All right, let's take a look at another example. Let's say AD equaled 6 and CD equaled 9. Could we find AB? Well, in this time, we are looking for a leg. And I remember that leg squared equals adjacent part times the whole hypotenuse. So in this case, x squared will equal 6 times 6 plus 9, or 15. So solving that, we see that x equals 3 root 10. All right, so suppose we had this figure at the left, and I told you that BC equaled 8 and BD equals 20. Could I find AB? Well, once again, we know that the leg squared is equal to the adjacent part times the whole thing. Solving for this, I see that 64 equals 20x, so x equals 3.2. Well, that can't be, because if the entire hypotenuse is 3.2, it couldn't have one part that was 20. That wouldn't make sense. So in this case, it's impossible. And that's something we have to be a little bit careful of with this formula. It doesn't always take into account situations that just don't work. So you got to keep your eyes open as you're solving. All right. There will be some problems in the textbook that are very much like this to give you some more practice. Okay, thanks for watching.